A lot of people are interested in space, astronomy, different planets, space travel, and so forth. And of course, it's a common subject in movies. There's a lot of physics involved in this sort of thing, and the physics is a lot different than what's often portrayed in the movies. But one thing we study in first semester physics is the mechanics of orbital motion, of motion from one orbit to the other. For example, we're in an orbit around the Sun, the Earth's orbit. We want to send a spacecraft to Mars. How do we get the spacecraft to Mars? What kind of velocity do we give it? What kind of direction? We don't just drive right over to Mars. We have to move within the gravitational field of the Sun, and the gravitational field of the Earth, and the gravitational field of Mars. Most of the trip, of course, the Earth and Mars are irrelevant, except that that's where we're trying to go from and to. And it's the Sun that really controls the mechanics. But we talk a lot about that sort of thing. Some interesting problems. A neutron star. A neutron star is a star the size of the Sun, which is about 1 million miles in diameter. But it collapses into something about 10 miles in diameter, and ends up as just tightly packed neutrons. You might know that atoms are mostly empty space, that there are just a few neutrons. If you were at the outer part of an atom, you almost wouldn't even be able to see the neutrons if you were at the scale of the atom. Of course, you couldn't see it anyhow because of the wavelength of light and so forth, but that's something we study second semester. But just the image. You got a lot of empty space with this little tiny speck of some neutrons and protons in the center. Those neutrons and protons and electrons all get crushed down to neutrons, and you have this thing called a neutron star with an intense gravitational field as you get close to it. Now, we can orbit the Earth, we can orbit the Sun. We do orbit the Sun, of course, on the Earth. The Earth orbits the Sun. Let's say we had a spacecraft that could go into the vicinity of a neutron star. Now, neutron stars are really not something you want to get close to because they're always sucking matter in, and as the matter accelerates, it creates X-rays and all kinds of nasty radiation that's going to fry you if you get close. But let's just say that we had a spacecraft that was capable of blocking all that radiation and all the thermal energy that's emanating out from the neutron star. Seems to have extremely powerful gravitational fields. Could we then orbit the neutron star and try to get a good look at what's going on? There's no radiation to fry us or anything. Well, it turns out you're still going to end up as Hamburger, no matter what you've got to shield you, as a result of the gravitational fields and the changes in the gravitational fields. That's kind of an interesting problem, although it's not a real interesting idea to contemplate actually trying to do that, because it would certainly be fatal and probably extremely painful as you got pulled apart. Okay, another subject that I more or less alluded to is bad physics in movies. I have to admit that I get easily distracted by bad physics in the movies. Even a great film like Star Wars, it bothered me to see these people in these spacecrafts making right-angle turns at 80,000 miles an hour, whatever speed they were traveling. I mean, if you're pushed into the door of the car as you go around a curve at 60 miles an hour, what's going to happen if you make a sharp turn at 80,000 miles an hour? It's not going to be pleasant. You're going to be pushed into the door is going to push back, you're going to end up as Hamburger again. I can kind of overlook that because, of course, you have to have this willing sense of disbelief. But in other movies, there's some really atrocious stuff. For example, splitting an asteroid the size of Texas that's closer to the Earth than the orbit of the Moon with a nuclear bomb. And the asteroid splits apart and misses the Earth on both sides. The two pieces don't rotate, and they split apart and miss the Earth. If you calculate how much energy it takes to make them, to accelerate them to a velocity where that would happen, and you calculate the energy of all the atomic bombs on Earth, doesn't come close. A lot of other examples. And it's kind of interesting to see how that works. And to see where the bad physics lies in the movies. It doesn't have to distract you, it doesn't have to ruin a movie. If you got a great movie like Star Wars, that's fine. You can just kind of say, okay, yeah, this is a cowboy western. They can't really do that, but let's pretend that it was possible. If it's a really bad movie, of course, then bad physics just detracts from a bad movie. And of course, good physics doesn't really help a bad movie. And you have to take a few artistic liberties. But we can talk about those sorts of things. Now, these are just selections of some things that are kind of interesting about physics, some interesting ideas, some interesting concepts, some things that you'll have a good handle on by the end of the course. Another thing is vibrations. How do you design the shocks in a car to avoid vibrating the car apart? If you design the shocks wrong, the car is going to pick up the vibrations of the road, and you're going to end up with a bunch of bolts laying on the road and you alongside them. A lot of very important applications. Another thing about physics is it teaches you a way of thinking analytically about problems, breaking problems down, devising valid and useful problem-solving techniques. The ability to conceptualize, the ability to apply mathematics to the real world. So these are some of the things that we're going to see in this course. We'll continue in a minute with another clip showing you a little bit more about the specifics and the structure of the material in the course.